Good morning, one and all. I welcome you back for the first session of this 1 week GAN course all about wireless power transfer, antenna circuit devices and applications. The very first lecture of this 1 week GAN course is to be delivered Professor Naoki Shinohara from Kyoto University, Japan. Before starting him to start the talk, let me introduce him formally. Naoki Shinohara received his BE in Electronics Engineering and ME and PhD in Electrical Engineering from Kyoto University, Japan in the year of 1991, 1993 and 1996 respectively. He joined Kyoto University as a research associate in 1996 and has been a professor since 2010. His research focuses on solar power satellite and microwave power transmission systems. He is a fellow of IEEE, fellow of URSI, an elected ADCOM member of IEEE MTTS 2022 to 2027, former chair of IEEE MTTS TC25, Technical Committee 25, chair of the IEEE MTTS Standard Committee, Region 10 MGA coordinator, and founder of the IEEE Wireless Power Transfer Conference and Expo, IEEE WPTCE. He has also served as chair of URSI Commission D, president of the Japan Society of Electromagnetic Wave Energy Applications, and president of Space Solar Power System Society. Professor Shinohara has authored over 140 journal papers, delivered more than 110 keynotes, and given over 150 invited talks, including 55 distinguished microwave lectures, DMLS. He co-invented 35 patents and has collaborated with more than 150 companies in wireless power transfer and microwave applications. His contribution has been recognized with prestigious awards, including the IEEE 2023 Journal of Microwave Best Paper Award, the 2022 MEXT Ministers Award Japan, and 2023 IEI CE Achievement Award. His students have received over 100 awards during 2011 to 2024. He chairs Japan's Wireless Power Transfer Consortium for Practical Application, WIPOT, and Wireless Power Management Consortium, WPMC, fostering academia-industry collaboration. His authored book include Wireless Power Transfer via Radio Waves, published in the year of 2014, Far-Field Microwave Power Transfer and Energy Harvesting, published by Arctech in 2022, and Theory and Technology of Wireless Power Transfer, published by CRC in the year of 2024. With this, I welcome you, Professor Naoki Shinohara, to start the first lecture of this GAN course.
So can you hear me? Yeah. So, pointer if you have. Yes. No worry. Just a pointer. I use it. Yeah, I understand. But
slide you can choose.
yeah, I know. But no worry. Yes. What? Oh. I know. But here you install this. And, I must. 言いたくないんだけど。Yeah. I know. I understand. So thank you so much. Thank you for waiting. So I'm Shinohara from Kyoto, Japan. So I really appreciate. I'm very honored to be here. So you have already heard a lot of my introduction. So I'd like to start my GN course all about the wireless power transfer. And so please check your program of this GN course. I a little bit arrange this course, but totally it's the same content, so don't worry about it. And in this program, first lecture is review and recent R&D of the radiative wireless power transfer first. And in this 1 hour, I mainly focus on the basic microwave theory and technology. I suppose you are all students of electrical engineering, or you have already learned electronics or radio wave technology or microwave technology, so on. But important point is in viewpoint of the wireless power transfer, wireless power. I suppose you've already learned technology of the radio wave or microwave to realize the wireless communication systems. So, of course, we use the same max resolution, and we use the same equivalent circuit, distributed line theory, or etc. But when we change our viewpoint from the to transmitting information to transmitting power, the same max resolution is changed. So in this 1 hour, as a basics microwave theory and technology, I'd like to introduce the same max resolution in viewpoint of the wireless power transfer. So, and next 1 hour in this afternoon, I will introduce R&D of the WPT application as a business and in space, the third lecture in this afternoon. So this is too much my introduction, so you don't have to learn a lot from this information. But I'm mainly working in the IEEE Microwave Society as a member of the standard committee chair, etc. So now, fortunately, in IEEE Microwave Society, wireless power is one of the hottest topics. So I'm very honored to work for the IEEE in viewpoint of the wireless power transfer technology. And recently, of course, I published a lot of papers, and here you can see these are books about the wireless power transfer. So now I published the 6 English textbooks of the wireless power transfer, and additionally 3 Chinese translated textbooks of the wireless power transfer, and additionally Japanese books. And when you visit Amazon.com or the other bookshop, online bookshop, you can find these textbooks of the wireless power transfer. And if you need to learn more after my talk, please check these textbooks. And there are very interesting textbooks, I think so. And first of all, I have to introduce Kyoto and Kyoto University. Maybe some of you know where Kyoto, but I suppose some of you doesn't know the Kyoto and the Kyoto University. This is a Japanese small island, as you know. Here is Korea, big China, or India is over there. And here is Kyoto Prefecture, Kyoto downtown here, about the center of the Japan island, Kyoto. And sometimes you confuse Kyoto and Tokyo. I suppose the pronunciation is very similar, and my English is not good. So, but Tokyo is the current capital of the Japan, and Kyoto is a very old capital, about 1,000 years ago or more. So please don't confuse Kyoto and Tokyo, different city in Kyoto, in Japan. And Kyoto is a very famous sightseeing place. So in winter, you can see snows, very beautiful snows, and it's a very famous Golden Temple in Kyoto. And autumn, of course, you can enjoy the very beautiful red leaves, and in spring, very famous Japanese cherry blossoms you can enjoy. But don't visit Kyoto in summer. Recently, by global warming problem, so summer in Kyoto is hotter than here. So, for example, last week I spent Kyoto under the close to 40 centigrade and very wet. So please visit Kyoto in winter, autumn, spring, except summer. You can enjoy sightseeing in Kyoto city. And this is a picture and information of our university, Kyoto University. I believe Kyoto University is one of the top university, national university in Japan. We have about 1,000 professors and over 5,000 employees. And students of undergraduate is 12,000. And we have about 1,000 master and PhD students in my university. And the most important point to show the importance of Kyoto University is the number of the Nobel Prize winners. So fortunately, from Kyoto University, there are a lot of Nobel Prize winners. Recent Nobel Prize winner from Kyoto University is he. He is also a professor, Professor Honjo. He is a medical Nobel Prize winner. And some of you know Professor Yamanaka of the IPS cells. They are the professor in Kyoto University. And the first Nobel Prize winner in Japan was born from Kyoto University, Professor Yukawa. He got the Nobel Prize about the theory of the atoms. I don't know the detail, but fortunately, over 10 Nobel Prize winners were born from my university. And we have 3 campuses. And this is a picture of the main campus. And I'm from the second campus in Uji, neighbor of the Kyoto downtown city. And in this Uji campus, we have 4 research institutes. There is no department of university in this second campus. But I belong to the research institute, and students in my laboratory are from the electronical engineering department from this main campus. So if you are interested in the wireless power transfer at the Kyoto University and the Kyoto, please ask me. So this is a brief introduction of the Kyoto and Kyoto University. And this is our research equipment in my laboratory. Here you can see this is a very huge anechoic chamber. We have 2 big anechoic chamber, especially for the wireless power. Here you can, it's not clear. This blue absorber in the anechoic chamber is a normal absorber. I suppose in this campus or in India, there are a lot of anechoic chamber for wireless communication test or the other. But here, this wall is black. And this is a high power absorber. If you transmit over kilowatt microwave into this wall absorber, they will not be burned. If you input over kilowatt microwave, it's like a microwave oven, and this novel absorber will be burned. It's very dangerous. But we install a very high power absorber in this wall. So in this anechoic chamber, we can carry out the WPT experiment safely. And additionally, we install the near field scanner in this anechoic chamber, and we have a beam controlling phase array antenna system for other equipment. So these systems are named AMET-LAB, Advanced Microwave Energy Transmission Laboratory. And this system, anechoic chamber, are open for everyone in the world. So if you would like to use anechoic chamber and phase array or the other, please ask me again, or please ask Professor Khan. You can use this anechoic chamber or the WPT equipment every day freely. So from here, I would like to introduce what is wireless power transfer. So it's very simple. This is a very simple cartoon. So we all use electricity and power. And we are always afraid the shortage of the battery. So electricity is the most important, like the air, I think so. And additionally, recently, wireless communication and information are important too. Of course, if you are from the internet, especially Japanese young students are very afraid they will be away from the internet. So wireless communication technology, the other important technology like the electricity. So definition of the wireless power transfer is very simple. Just we combine this technology, power on the wireless technology. So it's very simple. And we use electromagnetic field or radio wave to carry the electricity. So I'll explain the detail later. And this is a simple system of the wireless power transfer. Sometimes you focus on the wireless technology and antenna and propagation technology only, but we use a gigahertz or millimeter wave, radio wave to transmit our power wirelessly. Of course, there is no problem. But please don't forget conversion circuit technology from the electricity to radio wave or radio wave to electricity again. So circuit technology are important more compared to the radio wave propagation technology. So in this Jian course, I would explain all about the wireless power transfer means. Today, I'd like to introduce WPT review and applications mainly. We have 3 slots, 3 hours. And tomorrow, I'll focus on the WPT beaming technology, antenna propagation, etc. And on Wednesday, I focus on the WPT transmitter and the circuit technology. Please change your mind from the maximum execution to the equivalent circuit and the devices. And on Thursday, go back to the circuit again, but as a receiver. So after receiving the wireless power, we must convert the radio wave or microwave to electricity. So to Thursday, I focus on the explanation of the receiver rectifier circuit technology. And on Friday, it's a conclusion, and I would like to introduce a future perspective of the wireless power transfer. So this is the structure of this Jian course, and please enjoy my talk in 1 week. So please go back to the radio wave itself. This is the basic theory lecture. So as I mentioned at first, you all learn about the information and broadcasting technology on the radio waves. And sometimes some of you learn the radar or remote sensing technology as an application of the radio waves. So these 2 applications are the most of all radio wave applications. So no, okay, yeah. So market of the radio wave application almost all about the information and remote sensing. There is no discussion, but please don't forget most important application, microwave heating. In your house, I suppose in Japan, all students and all family has a microwave oven. And I suppose in India, you have the microwave oven in your room. So this is a very important radio wave application as energy. In this application, it's energy of heat. So we convert the microwave to the heat for food application. So at last, now we reach the energy conversion from the radio wave to the heat and WPT. Energy conversion, same energy conversion from the radio wave to electricity. It's the same technology. Only a difference between the microwave oven and the WPT is last energy status, heat and electricity only. So all radio waves and light and electricity are based on the Maxwell's equation. Please don't confuse. So some of you consider Maxwell's equations are mainly there to describe the radio wave only, but electricity and light or thank you so much, X-ray or the other, all electromagnetic waves can be described by Maxwell's equation. This is most important point from the viewpoint of the wireless power transfer. Sometimes you classify electricity is electricity, radio wave is a radio wave, and optical and light technology is a light technology. But all radio wave, light, and electricity can be described by the Maxwell's equation. This is the most important point. So it means radio wave is energy. I explain later. You know the Poynting vector from the Maxwell's equation. So this is a brief history of the radio science and the technology from the Maxwell. As you know, before the Maxwell's equation, there was no radio waves in the world, in space. So as you know, Maxwell combined the Ampere's law and the Faraday's law, and he predicted the radio wave itself by the Maxwell's equation. But before the Maxwell's equation, there is only the electric field, magnetic field, and light and optical technology only. But Maxwell find we can combine Ampere's law and Faraday's law to describe the combination of the electric field and the magnetic field. He predicted the radio wave is in the world. And after prediction of the Maxwell's equation, Hertz carried out the first radio wave generation experiment in the 160 kilohertz radio waves. And after generation of the radio wave by Hertz, Marconi, Fedesen was all scientific giant promoted the radio wave information technology and broadcasting technology, and you can use your smartphone everywhere and every day. So this is the most important right as application of the radio wave. And additionally, please don't forget the radio science. Einstein, Derringer, Van der Horn, Appleton, etc. They are the other scientific giant in the not IEEE, but USI, Union of Radio Science International Scientific Society region. And additionally, I'd like to add one line, power line, wireless power line. This wireless power history is studied from Nikola Tesla. I will explain the detail in the second talk. And William Bragg, this start the WPT technology by microwave technology, and he's my boss, most famous Japanese professor Hiroshi Matsumoto. It's unfortunate 2 months ago he passed away, but he promoted the wireless power transfer and the solar power satellite from the Japanese university, but he excited the wireless power transfer R&D in the world. So please consider all three historical rights of the radio wave application, wireless communication, and radio science, and wireless power transfer. This is a history of the radio wave technologies. And so first of all, I have to explain the definition of the radio wave. So radio wave is one part of the electromagnetic wave, and as I told you, and the electromagnetic wave is covered from the all electricity and light and the X-ray or the other. But one part of the electromagnetic wave whose frequency between the 10K to the 100 giga or 10 terahertz is named radio waves. Because originally this electromagnetic wave applied for the radios originally. And in Wikipedia, type of electromagnetic radiation with the longest wavelengths and electromagnetic spectrum, typically with the frequencies of the 300 gigahertz. So definition is not strict. So we sometimes confuse the electromagnetic wave and the radio wave, but this is a definition of the radio waves. And in physics, as I explained a lot, electromagnetic radiation consists of the wave of electromagnetic field propagating through the space carrying electromagnetic radiant energy, and it includes a radio wave, microwave, visible light, or ultraviolet, X-ray, etc. And additionally, what is microwave? Of course, it's just a definition. So this is not a strict definition, but on Wikipedia or the other textbook, microwave is one part of the radio wave frequency between the 300 megahertz to the 300 gigahertz. So sometimes I use the definition of the microwave with a frequency from the 1 gigahertz to the 30 gigahertz. So definition is not strict, but about a centimeter wavelength wave is defined as a microwave. So after finding the microwave in 40s and 50s in the world, we can apply the wireless power as an effective application of the radio waves. And this is a microwave application. Some of you know, now you all have the mobile phone. And recently, in 5G application, hopefully, we would like to use the 28 gigahertz. But in the real, you use about 3 gigahertz or 4 gigahertz as a 5G mobile communication. And the Wi-Fi is in the 2.45 gigahertz and 5.0 gigahertz and etc. So if there are no radio wave and there are no microwave, your life becomes very, very poor. So this microwave application and the radio wave application are very, very important for our life. I think so. So from here, I'd like to introduce antenna and propagation basic theory, mainly the maxillization. So as I mentioned again and again, so originally, before the Maxwell, we have Ampere's law and Faraday's law. You must know these formula as a student. And he combined this Ampere's law and Faraday's law, and he adds this term, the deviation of the D. So with combination of the Ampere's law and the Faraday's law and a little bit arrange these four most important maxillization were born in about 150 years ago. So this is we can describe all about the electromagnetic wave from the electricity, for example, 60 hertz, or a very low frequency, or microwave, X-ray, ultraviolet, etc. And but as I mentioned, we can use the radio wave is energy, but energy, electricity, you know, the other famous formula, Ohm's law. But there is no Ohm's law, it seems. But here, this is a very, very small equation describe the Ohm's law. So when we integrate this J as I current, and when we integrate this sigma, it becomes 1 over R, and E is integrated to the voltage. So in this maxillization, even the Ohm's law are involved. So this is very important point. So please don't confuse Ohm's law to describe the electricity and the maxillization to describe the radio wave are different. No, it's the same. Maxillization involves the Ohm's law, Ampere's law, and the Faraday's law. All. So most important theory is Maxwell's equation. You must know, and you must write without any textbook this Maxwell's equation. And this is an image of the solution of the electromagnetic wave by the Maxwell's equation. So electric field propagates into this line with change of the time and place, and the magnetic field is propagating in this line. But based on the original maxillization in combination of the Ampere's law and the Faraday's law, this image is similar. So first, electric fields create the magnetic field by Ampere's law. And this high frequency magnetic field recreate the electric field by the Faraday's law. And Ampere's law, Faraday's law, Ampere's law, etc. As a result, it becomes radio wave and electromagnetic wave. And after the finding the Maxwell's equation, the other scientific giant pointing indicate this Poynting vector Of course, you know this Poynting vector equals h. And unit of the Poynting vector is watt per square meter. It means radio wave, electromagnetic wave is energy, unit of watt. So here you can see combination of the electric field and magnetic field create the energy flux density Poynting vector S. So and here you can see the microwave oven. Based on the Poynting vector, we can heat up our food in the microwave oven. And this is other evidence of the microwave oven. Of course, we can heat up our food inside the box of the microwave oven. But when we convert, just a moment, we convert this microwave not only to heat but to light power. So this is a YouTube video. When we heat up the light inside the microwave oven, here. So microwave is converted to the light power. Please don't do it. It's very dangerous experiment. But it's one evidence. Microwave or radio wave, electromagnetic wave is energy itself. So heat energy, light energy, and electricity. It's the same. But additionally, we need a frequency conversion because as electricity, we cannot apply the gigahertz electricity because a semiconductor cannot understand the gigahertz radio electromagnetic waves. So usually, as electricity, we apply the 60 hertz in Japan or direct current mainly. But to propagate the radio wave in space, we have to apply the megahertz radio wave or gigahertz radio wave. So, but as I mentioned again and again, based on the Poynting vector, radio wave itself is energy, and it's the same as electricity. But only the difference between the electricity and the radio wave is the frequency. So we must convert the frequency from the hertz to gigahertz or gigahertz to direct current. So that's all about the wireless power transfer. It's very simple, most simple explanation. We need a frequency conversion in the Maxwell's equations. And this is other evidence, wireless power with the help of the microwave oven. This is a real patent in United States by the Philips Corporation. And they said they can charge wirelessly your smartphone inside the microwave oven. This is a real patent about 25 years ago. But please don't do that again. If you put your smartphone inside the microwave oven, of course, your smartphone will be broken. But there is a very few secret in this patent. So here, number 12, here, this is a Faraday cage. A Faraday cage is a very complex name of just a metal box. So metal can reflect the radio wave. So this metal named Faraday cage can protect your smartphone first of all, and and to create one hole here and an antenna to receive the microwave power outside of this metal wall. And from this antenna, we receive the microwave power. And here, number 26, half-wave rectifier. This is a receiver with help of the diode. So this diode can convert the microwave gigahertz radio wave to direct current. That's all of this pattern. So if we can realize this system, you can charge your mobile phone. About 25 years ago, at that time, our not smartphone, just a mobile phone can be charged within 30 seconds because microwave oven can transmit 1 kilowatt. You usually you charge your mobile phone with only a 5 watt or 10 watt only. So if we realize this pattern, we can charge our mobile phone with very, very short time charging time. But unfortunately, Philips cannot realize this system because problem is here, diode. So now there is no good diode to rectify over kilowatt microwave with only one diode. So of course, I'd like to introduce on Wednesday about the device or the transmitting technology or the other. And we have a wide bandgap device technology with the help of the gallium nitride or silicon carbide or gallium oxide or diamond, etc. But now, even in the 2025, there is no good wide bandgap diode to convert 1 kilowatt microwave to electricity. So this is just a dream by the Philips, but theoretically we can do it. So this is a very good example of the wireless power. And in advance, as a wireless power transfer system, when we put the rectenna, you cannot see this title, rectifying antenna, you can realize the WPT system with the help of the rectifier with a diode here. So this is a most important technology and device for the wireless power transfer because you receive the radio wave as a carrier of the information, and you use a demodulator or the other information circuit as a receiver. You don't use any carrier itself as a receiver in the wireless communication system. But we, WPT group, use the receiver as a converter of the carrier itself. So this is a special technology only in the wireless power transfer system. I'd like to introduce on Thursday, mainly. And based on the Ampere's law and the Faraday's law only, we can apply the inductive coupling wireless charger to charge our mobile phone. Or when we change current and voltage, the same inductive coupling WPT can be converted to the capacitive coupling. In inductive coupling, we use a magnetic field, but in capacitive coupling, we use an electric field. And we combine the Ampere's law and the Faraday's law. We can use a radio wave as a carrier of the energy, as I mentioned again. And additionally, in 2006, Massachusetts Institute of Technology Group proposed the magnetic resonance coupling WPT technology. After the revolution of the MIT technology, you finally, because I spent a long time, about 30 years, to carry out the WPT research. But before the MIT revolution, they don't mind our research and WPT research in the world. But after the revolution of the MIT group of the resonance coupling, all people consider WPT is a very interesting technology, and now there are a lot of commercial products in the world. And today, I'd like to introduce mainly the WPT via radio wave and microwave. But before moving to the radio wave, I'd like to introduce a difference between the near field inductive coupling WPT and the radio wave. And we named various words of the WPT in near field WPT and the coupling WPT and the non-radiative WPT. They use mainly the a few dozen kilohertz or megahertz order high frequency magnetic field. And what happens when the position is changed in the inductive coupling? So we optimize the frequency and the impedance of this coil to carry effectively the wireless power, and designed optimized coil to carry the magnetic field energy is very excellent, and the efficiency becomes max. But when this coil moves to somewhere, what happens? I explain now. This system is named the coupling WPT. And please imagine Ampere's law and Faraday's law. and two coils are electromagnetically coupled. So when this position of the receiver moves to somewhere, resonance frequency changes and circuit impedance becomes unmatched, and and efficiency decreases. So this is based on the coupling theory, based on the Ampere's law and Faraday's law. So in this case, we need to re-optimize these parameters of frequency and impedance, or etc. But so now there are a lot of inductive wireless charger products, and but in far field WPT, and sometimes we named it uncoupled WPT, radiative WPT, etc. What happens when receiver position is changed? So condition is the same. We optimize the frequency of the antenna, and circuit impedance is matched and optimized. And as a result, efficiency becomes max in the system. But when this antenna moves to somewhere, what happens? Unfortunately, there is no electromagnetically coupling. So unfortunately, transmitter side, cannot understand the change of the position of the receiver because there is no electromagnetic coupling. So resonance frequency is still matched, and circuit impedance is still matched, but beam from the transmitting antenna keeps in front in this case. So efficiency decreases, but we cannot understand what happened in this case. In the coupling WPT, it's easy to understand the decrease of the efficiency is caused by the change of the frequency or change of the impedance. But in the radiative system, unfortunately, frequency, resonance frequency, circuit impedance are the same, even if receiver moves to somewhere. So it's very difficult. So in this case, we need to keep in order to increase the efficiency, beam direction must be controlled, and we must check the target positioning. So this beam forming technology and target detecting technology are most important in the radiative WPT system. And on tomorrow, on Tuesday, I will explain the detail of this beam forming and the target detecting technology. So from here, I'd like to briefly, because I don't have enough time, so basic theory of the radiative WPT. So please go back to the Maxwell's equation again. And based on the Maxwell's equation, you can solve this Maxwell's equation of the number one and number two in combination. Maybe you can solve. It's easy to solve this Maxwell's equation. As a result of this change of the formula, so with the help of this formula, as a result, we can reach this solution of the electric field or the magnetic field. Sorry, I don't have enough time to explain more, but this solution transformed from the Maxwell's equation is most important in all radio wave technology, not only for wireless power transfer, but also the wireless information and the remote sensing technology. And we get the wave equation from the radio wave Maxwell's equation, and this is a general solution, and it involves the propagation in time and in the z direction here. So this figure again appears again, and this is an image of the propagation of the radio wave, all for wire communication and wire WPT or etc. But please don't confuse. This is an exact solution by Maxwell's equation. There is no doubt. It's correct. But sometimes you confuse because this K includes this formula. And this K includes attenuation constant and phase constant. And sometimes when you are a student of the electrical engineering or the radio wave engineering, you use the distant attenuation or the attenuation in distance. When we expand the distance between the transmitter and the receiver, you consider this in this long distance, attenuation by distance occurs. But usually in free space or in the air, based on this equation, sigma is equal to 0, and alpha as an attenuation constant is equal to 0. You've already learned in your class, I suppose so. It means there is no attenuation in the air or in space, but you use there is an attenuation by distance. So this is the most important point, important viewpoint, different from the wireless communication group. In the viewpoint of the wireless power transfer, there is no attenuation by distance because there is no attenuation constant in this case. But of course, in the rainy day or the cloudy day, we have a real attenuation constant here. So, but this is a real attenuation. But if without any rain, we can assume sigma is equal to 0, and the attenuation constant is equal to 0. It means there is no attenuation in the air in the radio wave propagation. So, so solution is here. So now from this equation, you can image the radio wave propagates like the arrow only in the z direction. But this is one part of the solution, and this is a real solution by the Maxwell's equation. So this radio wave from the source is expanded omnidirectionally, theoretically, because please imagine the Maxwell's equation. Maxwell's equation involves a rotation or the curl, combination of the electric field and magnetic field. So this is a real solution. This wave equation is just one part of the equation of the Maxwell's formula. So this is a real image, and based on this image of the omnidirectional propagation, this received power at one part of the area is calculated from the simple surface area of the sphere equation. So please calculate the surface of the sphere. It's easy to calculate. So radius of this square is just a d, we assume, and 4 pi d square over pt. So just equal omnidirectional propagation. And when we apply the antenna, we add antenna transmitting antenna gain and receiving area, and this becomes a phase transmission formula. And based on this equation, when d becomes larger, longer, received power becomes received power decreases, so your image is attenuation. But please go back to the original equation. No attenuation constant. So this attenuation by the distance is just diffusion or expansion only by the radio wave itself. It means when we put the inner receiver at the receiver point, we can receive theoretically 100% power from the source. This is the most important explanation in this today's talk. So, please don't confuse this equation. This is just one part of the solution only. And the image of the radio wave propagation is this, omnidirectional propagation. And based on this omnidirectional propagation, phase transmission formula is calculated. So this is the most important explanation in this talk. And based on this explanation, we can classify the field of antenna by distance. You usually use a far field region case, and in this case, distance is enough far from the power source, And this is named the Fraunhofer region, and we can assume the plane wave. So please go back to this Fritz transform formula. So when we put larger antenna, double, triple, or 10 times larger, we can receive the double power, triple power, 10 times larger power. But if we cannot assume the plane wave, this is a very strange equation, because if the power density is not equal at the receiver, when we put the double area, but we cannot receive the double power. So this is named the distance of the Fresnel region and the radiative near field region. And to increase the efficiency of the wireless power, we usually put the receiver at the radiative near field Fresnel region. And in this area, we can receive the theoretically 100% power from the transmitter, because there is no attenuation. I explain again. There is no attenuation in the clear days. Of course, in the rainy day, we have a real attenuation, but theoretically, there is no attenuation in the air. So in this area, we can reach theoretically 100% efficiency. I will explain the detail tomorrow. And additionally, we put a closer distance antenna becomes a coupling system, and this suddenly becomes an inductive WPT system. I will explain the next talk. And this is a basic parameter of the phase constant and the phase velocity, etc. But I don't have enough time, so please check it. I suppose you know where these parameters of the wave number, wavelength, etc. And this is the wave impedance in the propagation. And wave impedance is calculated by the ratio of the E field and H field. And this involves this parameter of the medias. And so Maxwell's equation are very perfect. There is no exception. It means as an engineer, we cannot do it anything based on the Maxwell's equation for wave propagation of the antenna technology. But we are engineer. You will be the engineer. So as an engineer, what we can do is on the Maxwell's equation is only to change the initial condition, the boundary condition. Initial condition is equal to the radiation source, and it means the antenna. And on the Maxwell's equation, we can change only the J here as an antenna current. So as an engineer, what we can do on the Maxwell's equation is only this one. So I don't like it, but this is a perfect theory of the Maxwell's equation. And additionally, we can change the boundary condition after the radiation in the propagation. And this is a condition of the refraction and the reflection based on these parameters. We can change these media parameters. Mainly, we change the epsilon in the dielectric base, so as we put the metal as a reflector. So that's all about the Maxwell's equation theory as an engineer. So I don't like it, but this is a real Maxwell's equation solution as an engineer. We can only change the initial condition and the boundary condition. So it means we have the antenna. We need the antenna to propagate the radio wave, not only for wireless power transfer, but also the wireless communication. But based on the initial condition and the boundary condition, as an engineer, we can change the shape of the antenna. But after the changing the initial J or the boundary condition, propagation is exactly same based on the Maxwell's equation, and we cannot control the propagation. So I don't like it. So and this is a radiation image from the antenna, but I have to skip. And this is one example of the antenna parameter of the ideal half-wavelength diode antenna. And based on this initial condition, we can get this electromagnetic field at far field. But when we put the receiver in near field, we can change this far field equation to this complex equation. And the antenna is a radiative resonator as an initial condition. And as you know, we have a resonator, and it is named a non-radiative resonator for bandpass filter, etc. And MIT group find we can fill the missing link between the radiative resonator and the non-radiative resonator of the resonator antenna. So this is an antenna for your smartphones. But this is not a good antenna. But if we develop the non-radiative resonator, we can apply this resonator as an antenna. So in conclusion, on Friday, I will explain the detail of the relationship between antenna, resonator, and resonative antenna in the resonance coupling WPT. And this is the definition of the antenna again. This is the focusing factor in front mainly compared to the omnidirectional propagation. And this is the directivity of the antenna, and we can focus the wireless power into one point only. But except this focused point, the other area of the radio wave decreases because total power is the same. So sometimes you use EIRP, equivalent isotropic radiative power, etc. And sometimes you consider we developed a 1 watt transmitter, and we bought, for example, 10 dB antenna as a gain. So as a result, this is a system of the 10 watt EIRP system. But please go back to again. This is very strange. Transmitter characteristic is only 1 watt. But when we add the 10 dB antenna, just in front only, EIRP is a 10 watt system as a transmitter. But 1 watt is 1 watt. So it's very strange definition of the EIRP. So receiving power seems to be gathered from the other area. So this is the other important point. In the WPT system, there is no gain. 1 watt is 1 watt. So we can convert this 1 watt in propagation in the circuit. And finally, we receive the below 1 watt only. But in wireless communication system, sometimes you receive the 10 watt EIRP from the 1 watt transmitter. It's very strange. I don't like it. But for the wireless communication, it's convenient. So, but please don't confuse. In the WPT system, we only use 1 watt is a 1 watt, no EIRP. And this is the definition of the antenna aperture. But tomorrow I'll explain the detail later. So today I don't have enough time. I skip it. Maybe. And this is a boundary condition in propagation. And this is a famous Snell's law. When we propagate the radio wave in the different media, in different epsilon, different mu, etc., this radio wave is bented or reflected. But this wave propagation is decided by the Maxwell's equation itself. So as a result, based on the Maxwell's equation, we can get this relationship of the input wave and the reflected wave and transmitted wave. And this is the same as a change of the border condition. So when we put the reflector, for example, like this antenna, we can control the antenna gain, for example. And from here, I would like to explain, maybe please give me 5 minutes more. Please change your mind from the propagation to the circuit theory. So next, I would like to introduce the circuit and the semiconductor basic theory. So this is a transmitter or the receiver sample in the circuit. And I will explain the detail on Wednesday and Thursday. But when we consider the maximization, of course, we can describe the all propagation in the circuit. But it's very, very complex because we must solve the curl or divergence or etc. So instead of the maximization, we change our mind from the field or epsilon to the voltage, LCR, and Z. So this is one example of the propagation in the waveguide. Based on the maximization, we get this electrical field and magnetic field inside the waveguide, for example. But at the same time, we can describe the same this propagation with L and L circuit element. So this is a wave propagation theory and wave circuit theory, and it's the same in the device. And this is one example of the semiconductor gallium arsenide FET, and this semiconductor can be converted to this equivalent circuit in combination with the LCR, etc. So when we have the equivalent circuit technology, we can describe the wave propagation and semiconductor itself or the line itself. And this is a microwave circuit theory, but maybe I don't have enough time. Yes, I have to hurry. So this is a comparison of the parameters in space. This propagation parameter is described as alpha plus j beta. But in online, instead of the epsilon, mu, sigma, we can put the RLC and G. So this is the same explanation, one by Maxwell's equation and one by line. And input impedance can be converted from the relation to the E and H to the V and I. This is a circuit theory. So based on the maximization, we use the Snell's law to consider the reflection of the different medium. But in the circuit theory, we can apply the different medium means the different impedance circuit, and it's the same formula to describe the reflection in the circuit. So when we connect the two different impedance circuits, reflection occurs, and this reflection is not a good parameter. So we can reduce the reflection to propagate effectively the wireless power, even in the circuit. So we need to separate the reflection. So how to consider the separation of the reflection in the circuit? We use S parameter. Maybe some of you know. This is a useful parameter to describe the equivalent circuit in the maximization. S11 describes the reflection ratio from input port to the circuit, or S21 is a power gain from the input port. So with combination of the reflection and the impedance matching, we use this Smith chart. So this is the circle of the constant R and constant X. And this is a unit circle, and at the center, reflection is 0 from this equation. And we put the circle as a constant reflection ratio, and at the edge, this indicates reflection is 100%. So based on this Smith chart, it's easy to understand the impedance and the impedance matching by the circuit theory. I don't have enough time there. So this is a principle of the Smith chart. Originally, it is started from the reflection ratio, but at last, this reflection ratio is converted to the constant resistant and constant X. And this is an example of the Smith chart when we change the frequency. Impedance changes like this figure, and at the center, it indicates impedance is matched and there is no reflection. And when we consider the impedance matching with the help of the open stub in the equivalent circuit, based on this theory, we can match this impedance via this YIA and O. So maybe of course, I'll finish. So this is the explanation again, this impedance match circuit. So I'm so sorry, I don't have enough time. So this is this lecture's conclusion. So in this afternoon, I will explain the lot of various WPT application as a business first of the afternoon. And next afternoon talk, I will explain the hugest application of the wireless power transfer, solar power satellite. And Tuesday, Wednesday, Thursday, I will explain the detail of the technology. So I'm so sorry I don't have enough time. It's time to close in this talk. Thank you so much. Of course, I stay here in this week, whole this week. So please find me and please ask me anywhere.
Okay. Thank you. Thank you, Professor Naoki.
Thank you so much.
We'll meet again at 2 o'clock. Thank you.
Yeah. Yes. Sorry, it's too much.